sklearn, linear model, TweedieRegressor. Description: a generalized linear model GLM with Tweedie distribution for the response variable. This model is particularly useful for modeling count data, where the response variable represents the number of events occurring within a given time interval or space. The Tweedie distribution encompasses a range of distributions, including Poisson, gamma, and compound Poisson distributions, allowing it to handle different types of count data with varying degrees of overdispersion. Inputs: X, a two-dimensional array representing the input features or independent variables. Each row corresponds to a sample, and each column represents a feature. Y, a one-dimensional array representing the target variable or dependent variable. This array contains the count data for each sample. Outputs: coefficients, a one-dimensional array containing the estimated coefficients for each feature. The coefficients indicate the strength and direction of the relationship between each feature and the response variable. Intercept, a scalar value representing the intercept of the fitted model. The intercept represents the expected value of the response variable when all features are 0. Predictions, a one-dimensional array containing the predicted values for the response variable based on the fitted model. These predictions can be used for various purposes, such as forecasting or classification. Steps: model initialization. Create an instance of the TweedieRegressor class, specifying the desired parameters. Model training: fit the model to the input data X, Y using the fit method. This involves estimating the model coefficients and intercept that minimize the specified loss. Function: prediction: generate predictions for new input data using the predict method. This involves applying the estimated coefficients and intercept to the input features. Metrics: mean absolute error may measures the average absolute difference between the predicted and actual values. Mean squared error MSE measures the average squared difference between the predicted and actual values. Root mean squared error RMSE measures the square root of the mean squared error. R squared R2 indicates the proportion of variance in the response variable that is explained by the model. Visualization plots: residual plots plots the residuals differences between predicted and actual values against the predicted values. This helps identify patterns or trends in the residuals, suggesting potential problems with the model. Prediction vs. actual plots plots the predicted values against the actual values. This helps visualize the model's performance and identify potential biases or outliers. Fine-tune parameters. Power controls the shape of the Tweedie distribution. The default value is 1.0, representing the Poisson distribution. Other values can be used to model different types of count data. Alpha, the regularization strength. A higher value increases the regularization effect, which can help prevent overfitting. Fit intercept specifies whether to include an intercept term in the model. The default value is true. Solver specifies the optimization algorithm used to estimate the model parameters. Uncertainty methods. Confidence intervals provide a range of values around the predicted value that represents the uncertainty in the prediction. Prediction intervals provide a range of values that captures a certain level of confidence, e.g., 95 that the true value falls within. Challenges and fixes. Challenge 1: overdispersion in count data. This occurs when the variance of the response variable is greater than the mean, violating the assumption of the Poisson distribution. Sample use case: analyzing the number of accidents on a highway over a month, where the variance is significantly higher than the mean. Fixes. Use a Tweedie distribution with a power value greater than 1.0 to account for the over-dispersion. Consider using a negative binomial regression model, which is specifically designed for over-dispersed count data. Challenge 2. Zero inflation in count data. This occurs when there is a higher proportion of zeros in the data than expected under the Poisson distribution. Sample use case: analyzing the number of purchases made by customers at a store, where a large number of customers made no purchases. Fixes: use a zero-inflated Poisson ZIP or zero-inflated negative binomial ZINB regression model to account for the excess zeros. Separate the data into two groups, zero and non-zero, and fit separate models to each group. Challenge 3. Nonlinear relationship between features and response. The Tweedie regressor assumes a linear relationship between the features and the response. Sample use case: modeling the number of website visits based on advertising spend, where the relationship may be nonlinear. Fixes: transform the features using nonlinear functions, e.g., polynomial terms, logarithmic transformations to capture the nonlinear relationship. Use a nonlinear model, e.g., decision tree. Support vector machine that can handle nonlinear relationships. Challenge 4. Collinearity among features. High collinearity between features can lead to unstable coefficient estimates. Sample use case: modeling the number of sales based on both price and discount, where price and discount are highly correlated. Fixes: remove one of the correlated features. Use regularization techniques, e.g., L1 or L2 regularization to penalize large coefficients and reduce the impact of collinearity.